Welcome back to the deep dive. Today we're zooming in, way in.
Yeah, we are looking at the invisible architecture of the material world.
Right, we're talking about molecular crystal structure prediction, or CSP, which I know sounds incredibly niche.
It does. It sounds like something only a handful of people in a basement lab care about.
Yeah, exactly. But before you tune out because it sounds like a geology lecture, let's set the stakes here.
Please do.
Why does this matter to someone who isn't, currently holding a test tube?
Well, think about an HIV drug called ritonavir. Back in the late 90s, this was a miracle drug. It was saving lives.
Right.
But suddenly, during manufacturing, the capsules started failing dissolution tests. They wouldn't dissolve. They were basically turning into little rocks in people's stomachs.
Wait, but the chemical formula didn't change though, right? Like
Yeah.
it was the same molecule. Right?
Identical molecules, the exact same ingredients,
Mm-hmm.
but the packing changed.
The packet.
Yeah, the molecules just decided to stack themselves in a slightly different pattern, a different crystal structure that was more stable but completely insoluble.
Wow.
They had to pull the drug off the market. It cost hundreds of millions of dollars and, frankly, threatened patient lives.
Just because the bricks decided to stack differently.
Exactly. That is the polymorph problem. You can have the same molecule, but if it packs into form A, it cures a disease. If it packs into form B, it's useless.
Or I guess in the case of something like organic solar panels, Form A conducts electricity and Form B does absolutely nothing.
Precisely. So the goal of this whole field, CSP, is to predict these disasters before they happen, to know how the bricks will stack before you ever build the factory.
Right. But historically, predicting that is, it's kind of a combinatorial nightmare.
It's been called one of the grand challenges of physical science for a reason.
Which brings us to today's focus and the main source for this deep dive. We are looking at a new generative AI framework called PackFlow.
Coming out of researchers at MIT and Samsung?
Yeah, and they claim to have cracked a big part of this bottleneck. And the hook here is that this isn't just another AI making pretty pictures.
No, not at all.
It's a model that learns to build 3D crystal structures from scratch and then uses reinforcement learning to teach itself physics.
It's a fascinating approach.
Yeah.
Combining the intuitive world of generative AI with the rigid, unforgiving world of physics.
So our mission today is to unpack how PackFlow uses things like flow matching and physics alignment to solve this massive puzzle. But to appreciate the solution, we really need to understand the problem better.
The relax and rank bottleneck.
Right. So how do scientists currently predict these structures? Why is guessing a crystal structure so hard? Can't you just put the molecules in a box and see how they fit?
You can try. That is the traditional pipeline. Imagine you have a suitcase.
Okay.
That's your unit cell, the repeating box of the crystal. And you have a bunch of clothes, which are your molecules.
Mm-hmm.
You need to fit them in perfectly, so there's absolutely no wasted space.
I mean, I've packed a suitcase before. It's annoying, but it's doable.
Sure. But now imagine the suitcase can change its shape.
Oh.
It can be a cube, a long rectangle, a slanted rhombus, that's the lattice, and you have to figure out the molecular orientation and the symmetry inside that shifting box.
Okay. That sounds significantly worse.
And the clothes aren't soft shirts. They are complex, rigid geometric shapes that lock together.
Oh, and you have to do all this in the dark.
Right, so how does anyone actually do this?
Well, the traditional way is you throw the clothes into the dark suitcase randomly. That's the heuristic search, using tools like Genaris.
Heuristic meaning like a rule of thumb, a sophisticated guess.
Exactly. Genaris might generate random candidates or rigidly press molecules together to guess good spots. Then you shake the suitcase really hard to see if everything settles into place.
Like trying to force it all to fit.
That's the relaxation step. But here is the massive bottleneck. To know if your packing job is actually good, you have to calculate its energy.
Because in physics, stability means low energy. Nature is lazy, right? Nature wants to be in the lowest energy state possible. But calculating that energy requires quantum mechanics, specifically density functional theory, or DFT.
Which is famously a massive heavy lifter in computing.
It is brutally expensive. You can't just check a billion random guesses with DFT. You have to rely on those heuristic tools to give you a good starting point.
And if your starting point is trash,
then the result is trash. If you start with a bad packing job, no amount of shaking or relaxation will fix it. You end up missing the real answer.
Because you started too far away from it.
Precisely. You need a better proposal engine. And that is exactly what PackFlow is.
Okay, so let's get into PackFlow's architecture. How does it actually generate a crystal?
It treats this as a conditional generative task. It takes a molecular graph, which is just the atoms and bonds, and it has to generate two things simultaneously.
Cartesian coordinates and lattice parameters.
Right. Cartesian coordinates are where the heavy atoms sit in space, and the lattice parameters dictate the shape and size of that repeating suitcase.
Now, here is a key innovation I want to dig into. They use something called flow matching,
Yes.
which, we hear a lot about diffusion models for image generation. But flow matching is different. Instead of just diffusing noise, it learns a vector field.
It's a brilliant shift. Think about how diffusion works. It starts with total noise and randomly wanders through the fog, slowly removing noise until an image appears.
Stumbling into the right answer.
Yeah, but flow matching learns a trajectory. Think of it like a leaf floating in a river.
Okay.
The river's current is the vector field. If you drop the leaf anywhere, the current transports it directly to the ocean. It doesn't wander, it flows.
So it maps a direct path from the noise directly into the data. That makes it faster and more stable for 3D geometry.
Much more stable. And they do something else with this that is just a fascinating technical detail. Independent flow times.
Right, they separate the clocks.
Yes. In a standard model, you generate the atoms in the box at the exact same time. But the unit cell, the box and the atoms inside it, settle at entirely different rates.
They're two different physical constraints.
Exactly. If you force them on the same clock, the box might shrink too fast while the atoms are still rotating, and you get a massive collision.
Like closing the suitcase on your arm while you're still folding pants.
Perfect analogy. By decoupling them with independent flow times, the performance improves significantly. It stops the model from creating physically impossible structures.
Speaking of impossible structures, there was another term that really stood out to me. Covalent bond attention bias.
This is crucial for maintaining the chemistry.
Because without it, the AI might just put atoms wherever it wants, right? It might rip a carbon atom off the drug and float it across the room.
Which turns your medicine into meaningless soup. This attention bias forces the model to respect the shape of the molecule by paying extra attention to bonded atoms.
It tells the AI that these specific atoms are a rigid family and have to stay together.
Exactly. And the stats on this are wild. When they did an ablation study and removed this bias, the clash rate, which is atoms crashing into each other, jumped from about 2.7% to 19%.
Wow, so it's absolutely essential. There's one more data hygiene thing to mention here. The unwrapped beta representation.
Oh, the Pac-Man effect.
Yeah. Because crystals are infinite repeating patterns, right? Yeah. So a molecule might straddle the edge of the box.
Right. Half of it sticks out the right side and wraps around to appear on the left side. Periodic boundary conditions.
But if an AI sees that, it just sees a chopped up molecule.
It learns that molecules are supposed to be broken into pieces. So PackFlow unwraps them during training. It ensures the model sees whole, intact molecules, so it learns smoother geometry.
Okay, so this is a really solid base model. It understands geometry, it understands bonds, it doesn't crush the atoms with the box.
It's a great artist. It can draw a crystal that looks right.
But looking right and being physically stable are not the same thing.
Not at all. And that transitions us to what I think is the coolest part of this deep dive. Physics alignment.
Right, because the base model doesn't inherently know physics.
No, it just mimics shapes. To teach it stability, they use a post-training stage using reinforcement learning, or RL.
Where the model acts as an agent.
Yes. It generates a group of crystal candidates, and then an environment scores them.
And in this case, the environment is a machine-learned interatomic potential, an MLIP, which basically acts as a very fast physics calculator. It scores the crystals based on energy and forces.
Exactly. Energy represents stability, low energy is good.
And forces represent strain.
Right. If two atoms are crammed too close together, they push against each other. That's a high force. You want forces to be as close to zero as possible.
Now, the way they train this is really clever. They use GRPO, Group Relative Policy Optimization.
Because if you just tell the AI an absolute energy number, it gets confused. A good energy score for a tiny water molecule is completely different from a good score for a massive organic compound.
So it grades on a curve.
That is exactly what GRPO does. It asks the model to generate, say, 10 different attempts for the exact same molecule.
Okay.
And then it asks, is candidate A better than candidate B? It just steers the model toward lower energy and lower forces relative to its own recent guesses.
Which prevents the AI from finding weird cheat codes to just artificially lower the absolute score.
It creates a much more stable learning environment. And they pair that with advantage mixing.
Because energy and forces sometimes conflict with each other.
Very often. You might find a shape that has great overall energy, but terrible local strain. Advantage mixing acts like a balancing dial. It allows the model to find a sweet spot where crystals are both stable and clash-free.
Okay, so we've got this fully trained, physics-aligned AI. The big question is, does it actually work better than the old Gennaris method?
The metrics are incredibly impressive. Let's start with density error.
Which is just guessing how tightly the crystal should be packed.
Right. PackFlow showed up to an 83% reduction in density error.
83%, that's huge.
It is. Gennaris plain tends to undercompress, making the crystals too fluffy, and Gennaris rigid press overcompresses, making them too tight. PackFlow gets it just right.
But the real test is the blind test.
Yes, the ultimate proving ground.
They tested it on unseen cases from the Cambridge Crystallographic Data Center, specifically OBQA, which is rigid, and XAFPA01, which is flexible.
And the outcome here really highlights the difference between a heuristic guess and an aligned AI.
Because even if the heuristic methods sometimes started with a lower raw energy score, their structures were fundamentally distorted.
Exactly. They were stuck in what we call local minima. They looked stable to the basic calculator, but they weren't the true physical shape.
High energy fakes?
Right. But when they took PackFlow's candidates and applied them to a rigorous relaxation pipeline, they relaxed into much lower energy minima, more stable, true forms.
It actually found structures within a few kilojoules per mole of the experimental reality, which the paper notes is the gold standard for accuracy.
It gave the physics engine a map that actually led to the destination.
And it does all this incredibly fast.
Inference takes about 0.1 seconds per structure.
0.1 seconds compared to days or weeks of heuristic searching.
It completely amortizes the computational cost. You spend way less time and money fixing bad guesses in the DFT stage because your initial guesses are so phenomenally accurate.
It's a massive force multiplier for the entire field.
It really is. PackFlow effectively combines the geometric intuition of generative AI with the hard constraints of physics.
So looking at the bigger picture here, this isn't replacing the expensive physics simulations.
No, it is a proposal engine. It creates a dramatically better starting line so those expensive simulations can actually finish the race.
We are moving from simply predicting what nature might do to having a tool that can actively design and align structures toward specific physical properties.
That's the leap to inverse design.
Right. Which makes me think about the timeline of discovering a new life-saving medicine. If you can predict the solid-state packing of a drug in 0.1 seconds,
You can screen millions of compounds for manufacturability before you ever synthesize a single one in a lab.
you completely avoid the return of your disaster.
Exactly. You save years and billions of dollars.
But taking that a step further, and this is something for you listening to really mull over, if an AI can perfectly balance these physics to propose how molecules pack, we aren't just limited to screaming earthbound drugs.
What do you mean?
Think about entirely synthetic materials, room temperature superconductors, or ultra-dense battery structures that nature would never naturally form on its own.
Oh, because we can dictate the exact pressure and synthetic environment to force a specific AI-verified polymorph to exist.
Exactly. If the AI tells us a miraculous crystal structure is stable under certain parameters, we could reverse engineer the manufacturing process to trap it in that state. We could literally architect alien materials atom by atom.
That is a staggering thought. The ultimate material sandbox.
It really is. The invisible architecture is finally becoming visible.
And programmable.
Well, thank you for joining me to unpack all of this, and thank you all for listening. We'll catch you on the next deep dive.